Now let's say that we have a tower. Let's say that this tower is actually pretty tall, tall enough to get above the Earth's atmosphere so we don't have to worry about atmospheric drag. What we want to do from the top of this tower is fire a projectile in the horizontal direction and see if we can't achieve an orbit, a circular orbit around the planet. Now this is part of a circle. We assume that this circle continues into a circular orbit. So we're going to try to do this. So we load up a cannon of some kind and we fire a projectile from the cannon. We don't fire it fast enough and the cannon, or the projectile is of course pulled down toward the earth in something like a parabolic arc, just like a ball rolling off the edge of the table. But of course starting out much higher, maybe with a much greater velocity, and landing hundreds of miles away. So we load up the cannon again, then we fire it faster. And we see that it takes longer to fall to the earth. And then we fire it really fast. We come out along this trajectory. Well, this trajectory is going to get pulled back toward the earth, but this trajectory is so fast that it stays above the circular orbit. Now, if we fire the cannon at just the right velocity, and let's move back here and see what's happening with the entire picture. If we choose just the right velocity, the cannonball falls, of course, but as it falls, the Earth keeps curving away from it. And there's a specific velocity for this height, and given the gravitational attraction of the Earth at this height, that this cannonball will continue falling toward the Earth, just as this projectile did and this projectile did, and actually just as this projectile does. But the rate of fall of this thing just matches the curvature of the Earth in some way. The circular approximation to the parabola that this forms just happens to be equal in radius to the distance from the Earth out to this point, if you want to look at it that way. Now this one that was fired too fast will travel out and out and out. The Earth is always pulling it back toward the center, which curves the path toward the center, and also slows the object down because the vector back in this direction has a component in this direction which slows the object down, and a component in this direction which causes the object, causes the path of the object, the direction of the object's path to change and to curve in toward the Earth. What's going to happen is this object is going to start out with a great velocity here, and then it's going to be slowed down and slowed down and slowed down to where it's hardly moving out here. And then it's going to start to fall back. Boy, things are falling all over the place here. It's going to start to fall back toward the Earth, and it's going to pick up speed and go faster and faster, and it'll come around the Earth and be fast, and then it's going to go away and be pulled back by the Earth to where it slows down and then starts falling back toward the Earth. So it'll follow a path something like this: fastest near the Earth and slowest out here. If we look at what's happening to the energy, of course, its potential energy is increasing as it moves further away from the Earth, and we can see that that's why. We can explain the slowing down from the energy conservation, that as we move away from the Earth, the potential energy increases and the kinetic decreases, and then as it moves back toward the Earth, the potential decreases so the kinetic increases. So again, we can see the slowing down and speeding up in this way. This, of course, is an elliptical orbit. There's one ellipse that happens to be a circle, so there's one circular orbit that we can have around here if we have just the right velocity. If we're going too fast here for a circular orbit, we'll end up with an elliptical orbit. If we're going too slow, we'll end up with an elliptical orbit. Right here is an elliptical orbit that gets interrupted, of course, by collision with the Earth and disaster for anybody who happens to be riding a spacecraft, if it's a spacecraft. If the Earth was a point mass, shrink the Earth down to, say, a black hole here, which would be about this big around, shrink the Earth into something about that size, it becomes a black hole. The gravitational attraction becomes so strong that not even light can escape it. Actually, light gets red shifted to the point that it no longer really exists, and will talk about that second semester. But we would have an elliptical orbit that goes in around this black hole very fast. Slow out here, but faster in here. So these are really orbits, but they don't quite make it because the Earth gets in the way.